So so far, the first 1/3 of the semester, all the materials we have covered, they are all rather algorithm solving technique oriented, right? You were taught a method that you can apply to solve a problem, and you saw examples on how it is worked out, what trouble you would run into, and then how do you deal with it. In the end, you get an answer to minimize some function over some constraint, and that's all fine. What we have not really touched will be some more in-depth analysis, in particular to show that the method really works, right? So for any method that you come up with, if it works for a couple of examples, that doesn't have any saying. If it shall stand in the history as one of the methods that later people will come and use, you must have some proof to show it works. Under what condition does it work? Is it general or not, right? Some theoretical stuff. So we'll get into that now, and maybe also for a week or two we'll talk maybe in a bit abstract setting. So after all, this is a math course, right? So are we expecting to prove things here? Yep, nope. Okay, so this is the chapter 3.8. I will give you a proof for the convergence of this simplex algorithm. Okay, so we'll specify what do we mean by convergence here. Okay, so it's all about proof. I give you a lemma, I give you another lemma, I give you a theorem, and we try to prove it. Okay, question?
I just wanted to double check. So everything that we're going to be covering for a while is not in the exam anymore, right?
No, that's right, yeah. So what we'll cover today will be for exam 2. Yeah, and possibly for final. Yeah. Okay, so we want to show that this technique that we have been using, that is, start from a canonical form, and then pick a good point and pivot, and then pick another point and pivot, eventually will give you the minimum of z, or will solve the problem in some sense. Okay, so let's put this up. We start with the canonical form, right? So let's write that. Okay, so let me put this standard canonical form here. So minimize z with the following. I have x1. It's in canonical form, so these are my basic variables, and then I have the non-basic ones, a1 n plus 1, x n plus 1, all the way to a1 n, x n is b1. So I'm going to just do the last one, and that's b m. So these are the constraints. And then you have your objective function written in terms of non-basic variables. So let's pick that up. C. These are called C's. And Z0 plus C, right? And of course, non-negative. So that's the canonical form. That's the starting point of the algorithm. Okay. Okay. So this I will label it. That's system 1. That's just a standard canonical form. Now we did touch up on this issue earlier. There was a class, a section, a chapter in the book called Theorems of Simplex Method, where we proved 3 theorems. Theorem O, the Optimality Theorem. Theorem U, where the mean is unbounded below, right? And Theorem M, where you actually perform one step of pivoting. Do we remember those 3 theorems? They're important. Okay, so over there, actually, we already discussed the convergence of this algorithm. Our discussion was restricted to a case that no degeneracy occur. That is, during the pivoting process, all these b's, they're always strictly bigger than 0. So after one pivot, you actually reduce the z value at a new basic solution. Remember that? And then because each time z is strictly decreasing, then each time you will end up with a different basic solution. And because the finite number of basic solutions, the number of basic solutions are finite for any problem, it has to converge after finite steps. Is that right? We did have that, so I just want to remark, we already have it. So if I is non-degenerate, okay, meaning the b's will never be 0 when you pivot, okay? So we already have convergence. We proved that. Convergence is proved already. There's no problem because you strictly reduce the z, and then it has to reach minimum at finite steps. Okay. What we want to consider now will be the general situation, in particular where degeneracy will occur, meaning the b will be 0 at some point, and we need to figure out how to deal with it. Okay? Is that clear? Okay, so we consider the general case. Okay, let's put some notation here. Well, I might not be so strict. So all these coefficients, they are called a and b and the c, and then we perform pivoting step. After each step, all these numbers could be different, and we'll still call them a or b or c. We just put a star on top to see that's a different number now. Is that okay? It's just a notation. So we'll use a star ij, b star j, or c star j, whatever, these to denote coefficients after or in the process of these pivot. Okay, just to show now it's a different number. Okay. So before we get into the proof, we need two technical lemma. Actually, two lemmas seemingly very obvious, but actually very useful. So let's state them. First is lemma A. Let's label them so I can refer back to it. Okay. So this talks about the pivoting process. In particular, deals with the B on the right-hand side, if it's 0 or not. So the lemma contains two parts. First, if I shall be in the situation that is the right-hand side, all these b's are 0, okay? For all I in the problem 1. Okay, then after one pivot step, what can you say? What do you think will happen to the b's? If I pivot, will the b be changed? Whichever equation I pick up, the b will be 0, and then I will be adding 0 on all other zeros. So all the b's will still be 0. Is that right? Do we agree? All right. For all I. Is that okay? That means for all I. Okay, is that obvious? Now, the second one. If I'm in the other situation, if now at least one of the bi does not equal to 0, actually we know it's strictly positive because it's feasible, right? If strictly positive, then what can you say? After pivot, one step, what do we have? What can you conclude about the b's on the right-hand side? If one of them is non-zero, after pivot, let me ask, does the same claim still hold? Can I claim at least one of them will not be zero? Do we agree? If I pivot on the one that's zero, then this non-zero is not changed. If that one shall be chosen to be pivot, and then he's not changed either. Is that right? Okay. We still have the same, at least one bi does not equal to 0. Okay, I should have star on that. That's after pivot. Okay, this I does not necessarily equal to the same I. So let's call bj for some j. Is that clear? I will not write down the proof now. I will assign this as a homework. Okay, so in the homework, make your best effort, argue that these two statements hold. You already see that they hold, right? Just write it cleanly, nicely that it holds. Is that okay as a practice of arguing? Okay, so that's the first lemma. Will be very useful. And I have a second lemma. Call it lemma B. Okay. Okay, it still talks about this pivoting process. Okay, now let's say I assume at least one bi is strictly positive. In the problem, we're always talking about the first problem now, the linear programming there. And I also assume that then I try to solve it with pivoting, and I find a sequence of pivot steps that solves the problem 1. Okay, so that's the assumption of this lemma. Okay, so one of the b is not 0, and I managed to solve it. Maybe I got lucky during the pivoting. I always got the one that's not 0 on the right-hand side, and it's z is strictly decreasing. So I solved it. This actually has dual meaning. One would be I could apply the optimality theorem that the z minimum is found, or the unbounded theorem can be applied. I conclude the z minimum is unbounded, right? Those two situations. I run into one of them. I finish the problem. Okay? Assume that is the case. Then I take the same problem and I change the right-hand side, put all b's to be 0. Okay? If we replace all bi's with 0, then I claim that the same pivot sequence can be used to solve it. Do we agree on that? So if one of the b is not 0, I have some sequence, I solved it. And now I replaced it with all 0. So think in the pivoting process. When you do the pivoting process, when you change some b values here, does it affect any of these c's and any of these a's? It doesn't. Is that right? All it changes, it might come here and change the z0 value. Is that right? In the tableau, because you add them vertically. So if the other process, say, you find the minimum of z, meaning all the ci's will be bigger than or equal to 0, then you change this b into 0 and do the same process, you will still reach a point where all the c's are bigger or equal to 0. You can still apply the optimality theorem. Is that clear? Do we see that? This is an important lemma. Okay, so I will not ask you to write a proof of it if you agree that it's obvious. Okay. Now let's state the theorem. That's the thing we'll spend the whole class today trying to prove, if we can finish. Okay. Okay. So now in the textbook, this is written like half page long and with a lot of details. Let's be just not that formal, rigorous. Let's just write out what essentially it's saying. It is saying for the linear programming problem in the canonical form, with or without degeneracy, we have the following. There exists, you can always find a sequence of pivot steps. So you can always perform pivot in a way. When I say sequence, that means finite, okay, not infinitely many. Okay, that solves the problem 1. So what do we mean? We need to elaborate. That means, when do we know we solved the problem? This means we could apply those two theorems, either theorem O or theorem U can be applied. Is that right? Either we reach the optimal z-min, or we conclude z is unbounded, and then we finish the problem. Okay? So let's recall those two theorems. Do we still remember? Theorem O, the optimality theorem. How do we know we reach the z-min? We check the coefficients, right? We check all those c's here if they are positive. So all of these c after pivoting of I are bigger than 0. Then you know z-min is reached. Is that right? Then that's how you stop. And then theorem U, how do I know that my z will be unbounded below? What's the condition? So theorem O doesn't apply, meaning I find some c here. We call it ck, which is less than 0. And I check the column of all the a's, and they're all less than equal to 0. A, ik less than equal to 0 for all I. Okay? And then if that is the case, and then you know the z-min is unbounded, it goes to negative infinity. Is that right? Do we remember those two theorems that we applied? Okay. Okay, so we're going to attempt to prove this theorem here by using those that we know. And in particular, we will use heavily those two lemmas, lemma A and B. Okay, they'll help us along the way. Okay, so let's construct the proof. Okay, so this is a rather seemingly very general claim, because I just have m equations and n unknowns, and just that, there's not even assumption of non-degeneracy. I want to prove that whole thing. Okay. So the technique that we will apply here, well, because the number of equations is an integer, and we intuitively see that if I have small numbers of equations, probably the problem is easier. So that kind of rings a bell. How about induction? Can I prove it for one equation as a base, and then I use inductive argument? All right, so that's what we will be using. Okay, and the inductive step will be applied on this integer m, that is the total number of equations, okay, by induction on this number m, which is number of equations. Okay, So are we all familiar with an inductive argument? What do you need to begin with? You need a base. You need to show for m equals to 1, this works. And then you perform this very heavy inductive step. If we assume it works for m for a smaller number and we increase m by 1, it still holds, then it holds for all m. Is that right? Okay, so that's what we will do. So okay, we need to take care of the base. The base argument, the case where for smallest possible m equals 1. So what does that mean? Well, I have only one equation, right? So this means only one equation in the problem. Okay, so let's say, just to fix the idea, let me just write out this equation. Would that be okay? I'll write out. I have the following. I have just one constraint, let's say, is x1. I'll copy the rest. A1 m plus 1 xm plus 1 plus a1 n xn equals to b1. Okay? And they're all positive. No, I don't need to write that. The positive t, let's don't write. Let's just write the objective function. C okay, so it's understood all the variables are non-negative. So let's say that's the one I need to deal with. I need to show that I can find a sequence, a finite many steps of pivoting process that can solve this problem with just one equation as constraint. Is that clear? So I want to prove that. Okay, and then there are two cases, because you know the good case is that if it's not degenerate, then I already know I can show it. And if it's degenerate, then I have to deal with it. Okay, so we have actually two cases. Let's list it up. Let's call it little a and b. So two cases. If I'm in the lucky situation, bless you. If now, not bi, b1, that's the only b here. If b1 is strictly bigger than 0, that's not 0. What can I say? After a pivot step, what will happen to b1? Will it become 0? Lemma A says, if at least one of the b is non-zero, then at least one of the b is non-zero. I have just one b. That b can never be 0. Agree? So, by lemma A, we conclude that b1 after pivoting will never be 0. Is that right? So no matter how many times you pivot, it will never be 0, meaning you never run into degeneracy. Is that clear? Every time you will strictly reduce the z value. So you're in the case of non-degenerate. It's always non-degenerate. And then, you know, simplex converges in finite many steps. That case we already proved. Okay, so that's the good case. And now, if I'm not lucky, I have b1 0, what can I do? How can, let me rephrase, how can any of those lemma help me? In particular, lemma B. How would that help me? Anybody? If bi is non-zero, I have a sequence. And now I set b1, now set b1 to be 0. By lemma B, I can still use the same sequence. Is that right? Of pivot step. That will conclude the problem. Is that what this lemma B says? Is that right? Mm-hmm. Let's do that. By lemma B, okay, same sequence of pivot will solve the problem. We'll solve it, and then we're good. Is that clear? Mm-hmm. Okay, so now we have established a base. Now we can start the inductive step. So, induction step. Okay, so what do we need to prove? So, okay, so now we have to make assumptions. So with the assumption of the inductive step, so assume the statement, what we're going to prove, holds for a smaller number, let's say for m minus 1 or less equations. Okay? Assume that if I have m minus 1 less equations, I can find a finite sequence of pivoting that solves the problem. And then I need to show this would imply if I have m equations, I have the same thing, right? So then need to prove it for m equations. So keep that clear, okay? That's what we're going to do. And it's a long process and takes many, many steps, okay? So you know that degeneracy plays an important role here. So let's look at the first case, case A. That is, I do not run into complete degeneracy. So that is the case. Assume now I am in the situation that among the m equations, okay, I'm considering this system of m equation now, okay, we have that at least one of the right-hand side b, bi, is not 0. Is that clear? So we will establish this inductive step for this first. Is that okay? And then if it's all 0, we'll deal with that later. Okay, let's say we have that. Okay, so one of them is not 0, which means I could apply pivoting. Maybe the one non-zero will be the one that I picked, and I could reduce the z-value at the basic solution by pivoting. It's possible to do that, right? So let's say I applied many steps of pivoting, try to reduce the z-value as much as possible until I get stuck. I cannot do it anymore. Is that clear? So there are several steps here. So let's say step 1. Okay, so what do? I apply my simplex method that we know. Many steps, okay, until we cannot do more. So until we can't pivot further to reduce z. Okay. So what do we mean by that? There are still two situations here. So the first case will be you manage to find the z minimum, or you solve the problem. Then you don't have to do it anymore. Is that right? So the case is solved. So the problem is solved. It could be. So meaning either you could apply theorem O, or you could apply theorem U, then you're done. So this is a good step. Then you're done. If it is solved, then you have a finite many sequence of pivoting, and you're done. So we only need to deal with the case that is not good. So, or you're in the other situation that the problem is not solved, but if you pivot, you cannot change the z-value. You cannot make it smaller. How could that happen? If you pivot one step, you pick that equation to pivot, and then you add this on top of z, and you cannot change it. What does that mean? That b is 0. Is that right? You have degeneracy. That's the case, right? OK, so now we have to deal with it. OK, or we'll have degeneracy OK, that is some bi's are 0. Is that all right? So I know I have some bi's are 0. So let's say, now I denote a number r equals to the number of 0 bi's. OK? So we know it's at least 1. So how big can this r be? Do you think I can have all the bi's equal to 0, that r equals to m? Can that happen? I would like to establish an upper bound for this r. So where do we start? At least one of the b is non-zero, right? OK, I always have to go back to the lemma. If at least one of them is non-zero, lemma A says at least one will be non-zero after any pivoting, which means at least one of the b will be non-zero, which means r shall be strictly less than m. Is that clear? So by is that lemma A, we can conclude that r should be strictly less than m. At most, m minus 1, right? There has to be one b that is non-zero. OK, so that's the first step. OK, now what I'm going to do, OK, now I have a bunch of zeros on the right-hand side. I'm still in canonical form. What I will perform, I will rearrange my equations. I will sort them out so that all the equations have 0 on the right-hand side will be on the top, and the one with non-zero on the right-hand side will be on the bottom. OK, I just rearrange them. And I can rearrange the indices of my axis so that the basic variable now will still be the first few and in that order. OK, so I'll write out. So what I will do is rearrange equation numbers and indices of the axis, OK, such that I have the following, that is bi equals to 0 for 1 less than I less than r. That's all the 0 on the right-hand side, and bi strictly bigger than 0 for r plus 1 less than I less than m. I can do that. Just rearrange them. OK, so let me write out the new system now. So I have the following. So I have x1 all the way to xr. Those are the equation with 0 on the right-hand side. OK, so let me put dotted line to separate it. Those will have 0 on the right-hand side. And then I have xr plus 1 down to xn. Those will have non-zero on the right-hand side. Is that right? And then I have the non-basic variables. There will be something here. So a1 m plus 1 x m plus 1. Those are not important in my argument. So I know the right-hand side is 0. I know this right-hand side is 0 as well. OK? And then for this equation, r plus 1 m plus 1 x m plus 1. It doesn't really matter what we have here. And then I will have b r plus 1. What I do know is that's strictly bigger than 0 by my way of arranging it, right? I put all of those down here. OK? Come down, and then I will have b m, which is strictly bigger than 0. Is that clear? I just rearrange things. I can write it like that. OK? So let me cut this up also, dotted line, so to see clearer. So this now, I call it my system number 2. OK, I should put star on everything. These are changed B's. OK. They are changed. OK, I'm not strict with that. So you know what I mean. These constants keep changing as I pivot. All right? OK, so, and I have the objective function, Cm plus 1, xm plus 1, plus all the way to Cn, xn equals to z0. These are stars, plus z. That's my objective function. OK, so I'm going to consider the first R equation with 0 on the right-hand side. I call these the star. These are our equations, OK? And then the last one, that's the objective function. Can I call it O here? I can say, so that equation, I refer to it as equation O, the objective, the condition here. OK. OK, so I enter the next step. OK. So here now, I am going to consider the following problem. So consider the problem with only the first R equation plus the objective function. OK? So you see that the star here is in canonical form. Is that right? I have the basic variables from x1 to xr. Is that clear? Because the way I arrange it, right? And these are non-basic variables, and they are represented by your objective function. So this thing here is a linear programming in canonical form. Is that right? So this is canonical form. And how many equations do I have for this problem here? With R equations, where we already know this R is less than or equal to m minus 1. Is that right? OK. Can I solve this? Did I assume I can solve it? My inductive step assumption, I assume that if I have m minus 1 equation or less, I can solve it. Right? That's the assumption. OK, so let's put that assumption by induction assumption. So what did we assume? The statement is true, meaning I can find a sequence of pivot step, finite number, that will solve the problem. Is that right? So this means, we have a sequence of pivot that solves it. OK, that's what I assume. So I would use that to show I can handle the whole thing, the system number 2, with m equations. Are we OK? Are we lost? Are you still following me? Anyone still hanging there? Hold on to it. OK. Let me erase this. OK, so the next step is the following. OK, so you know, OK, so now you have a sequence of pivoting. You will be pivoting only those axes, picking these equations that you could solve star plus O. Now what I will do will be I will take the same pivoting sequence and apply on this system 2, with the rest of the equation also tagged along. Is that okay? So that's what I would do. So apply the same sequence of pivot on the whole system too. Okay, so if I do that, what will happen? What do we expect? So first, let me ask you a question. What about the z0 value? If I do these pivoting, will the z0 value be changed? I will be pivoting one of the first R equations with 0 on the right-hand side. Would it affect the z, the column where the z is? No, because you would just be adding zeros on top. Is that right? So I know that this is unchanged. Okay? So after performing this, the same sequence that you did in step 3, you will be in the following situation. So we still have two different cases here. So, okay, so remember, what is this sequence? This is the sequence that solves the small problem, the first R equation plus the objective function, right? When we say it solves it, it means two possibilities. One is you find the z-mean. The other is you conclude with that constraint, z-mean is unbounded, right? Those two cases shall be handled differently. Okay, so let's look at these two cases. So can I use little a? There's so many numbering, ordering. Okay, so in the A, let's say that's the favorable situation. Now, after all these pivoting, I found out that C, all the coefficients there are bigger than equal to 0. Because those are unchanged by adding these into the pivoting process, because these will only be changed by those numbers that are up here, right? If that is the case, then you know you can apply the Optimality Theorem O, and then you can conclude I have found the z-mean. Is that right? The negative of that, and then you're done. And then you have found a sequence that solved the problem. Okay? That's the good case. Okay, and then what if we are in the other situation that actually when I solve the small problem with the first I equation of objective function, I actually have the other conclusion that I use the theorem U, that is the following. So for some Ck, for some index C, which now is negative, we have all these A, I, K star is less than equal to 0 for the first R equations. That's how we could stop in step 3, right? We're taking the first R equation and the objective function. If that happens, and then theorem U applies for that sub-problem, and then we stop. So if that's where you stopped, what do you do? You still have two cases. Now I'm running out of indexes. So, okay, let me just do dot. Let me just do a. Okay, what should I put? Okay, just a bullet. So it could happen that you're still in two different situations. You could happen that we have. So you're in this situation. After some pivots, all these C's, there is one that is negative, and you check all these A here, they are less than equal to 0, right? So now you need to check these A's, right? If also all of them are less than equal to 0, then you can still apply theorem U. Is that clear? Okay, so we have also all the a I k less equal to 0 for all the i's between r plus 1 and m. Then this is the case where you can apply theorem 2. And then you conclude the z min goes to negative infinity, and then the problem is finished, and then you're done. Right? That's also a favorable case. Then you're finished. You have find a sequence that solves the problem. Okay, but it's the other case that needs more argument. What if now we actually have some of these a's here that is positive? So we have for some I between that. Actually, we have a I k star strictly bigger than 0. Then what do you do? What would you do if you are in a step like this? You find one of the c that's negative, and you check in this column of a coefficient, and you find some of them are positive. Then you apply theorem M, you perform a pivot step. Is that right? Is that clear? That's what we do, right? So here you would apply theorem M and then perform a pivot. Okay, now here comes the most important argument for this step. So that place you're going to choose to pivot will be in the lower half of this system, because it's one of these a's that are positive, which means the b, associated b, will be strictly bigger than 0. Is that clear? Which means the z value at the new basic function will be strictly decreasing after you pivot. Is that clear? That is very, very important. Okay? So you know the associated bi will be strictly bigger than 0, and then you know z will strictly decrease. Is that clear? At the new basic solution. Okay, so let's take a break and check what we have achieved so far in this step A. So we have shown so far we have a finite steps of pivoting, finite sequence of pivot step so far in this case A, such that either I finish the problem, optimality theorem applies, unbounded theorem applies, or I strictly decrease the z value. Is that right? This sequence will do that for me. Okay? Okay, so now if that happens, then that gives me the idea I could repeat this process, couldn't I? So here's the final step. Step 5, in the case A. I will repeat 1 and 4 multiple times as I need. And then each time, I will either finish the problem. If I don't finish, z will be strictly decreasing. And then the same argument we used for the non-degeneracy can be applied. If z is strictly decreasing, this can happen only finitely many times. Is that clear? Okay, so let's write each time I have either complete this problem, complete the solution, or reduce z value, strictly reducing. Okay? So then it's easy to conclude if this is strictly decreasing, then this can happen only finitely many times. So which means infinitely many steps, you will have solved the problem, for sure. Is that clear? So this is what we want to prove. So this proves the statement. Okay, and then you can write now, by induction, the theorem holds for all m integer, right? Under the assumption, we still put an assumption that at least one of the BI is not 0. If that is the case, I prove the theorem. Is that clear? Are we okay? Okay, but then we still have to fill the last hole. We made an assumption that one of the BI is not 0. What if all the BIs are 0? Then this argument doesn't work. Is that right? We need something else. So with the final case, finally, if now all the BIs are 0, what can I argue? I think in one line I can finish it. Anyone wants to comment? You want to check the two lemmas we put up at the beginning? There is one lemma in particular says about if I put all the b's to be 0, then lemma b. If b is not 0 for one of them, and I have a sequence that solves it, then if I replace the right-hand side to be all 0, the same sequence will solve that problem as well. Is that right? Just that. Then you're done. There's nothing more to say, right? All the work we did in A will be recycled here. Okay, so by lemma B, I could use the same sequence. The same sequence will solve it. All right? Then we proved all cases. Is that right? Then it's done. Are we okay? Any questions? Comments? Okay, let's look back at the theorem, and in particular the way we proved it. So what did we prove, and what exactly the theorem says? This is a theorem that's a theoretical result. The theorem says there exists a sequence that will make me achieve this goal, to solve the problem. Is that right? And in the proof, we proved that. But you can look into the proof, and you see that it actually does not really tell me how to construct this sequence once given a specific problem, right? It's like an existence proof. It's not really a algorithm building proof. So let's put some comments here. Leave the statement of the theorem. Or remark. Let's put some remarks. Okay, so we want to remark. The theorem or the proof of the theorem we have shows the existence of the sequence of pivots. Okay, but it doesn't really give you a construction, but not a real construction of it. Okay, it just shows you there exists such a sequence. It might not be unique. There are many ways, but you can always perform pivoting and finish the work. So actually, this theorem gives us something more. So what does it say? So for the linear programming problem, the theorem says I can always find a sequence that solves it, right? So in the end, it's telling you that the initial linear programming problem can always be solved. So it says there exists a solution for that problem. Is that right? So that's a consequence of this theorem. So let me put that up. So this also proves the existence of solution to the linear programming, original linear programming problem. Okay, so usually something that is an obvious offspring of an existing theorem, we will call that a corollary. Okay, it's like immediate consequence. So let's state that. Corollary of the main theorem here. Okay, so of course you have to put some assumptions. And otherwise you cannot state anything, right? So if now I have if a LP problem has feasible solutions, so that's important. And I should know that for some reason, I know the objective function is bounded. Okay. And then you know there should be a minimum. A minimum shall be attained. Okay, so then there exists, okay, I would say at least one basic solution, which is feasible, of course, at which the z attains its minimum value. Okay? There might be multiple of them, but this shows at least one, because by going through the sequence you discovered in theorem M, you will at the end up at some basic solution. Is that right? And that's where the minimum of z will be found if it's bounded below. Right? Is that clear? Yeah. So, any questions? Are we okay? So this middle part is probably the most theoretical part. So next class, we will go into this concept of convexity. All right, so I will not strictly follow the textbook. I will add a few more things just to elaborate a little bit, because the convexity is a big deal in many, many mathematical problems. If a problem is convex, then you have a whole set of beautiful theorems. You can prove anything. It's like magic. So we'll take a peek at that and try to appreciate what it brings by being convex. Is it okay? Any questions? So I don't intend to go into that today, so we'll stop here.